Well, hello and welcome to lesson 23-4 practice. We are on page 328 in our text, looking to review lesson 23-4. So let's begin. Number 5 says solve each triangle. Remember, although that sounds rather vague, solve each triangle means find all unknown measures. So if we don't have 3 side lengths and if we don't have 3 angle measures, we need to continue to do what we call solve each triangle. Notice it says round all side measures to the nearest tenth. That's very important to note. And all angle measures to the nearest degree. So we're going to round sides to the tenth, angles to the degree. So let's take a look at 5A. Now, depending on the amount of space I actually have, definitely have to be working up here in the My Notes section. And I might even have to erase a little bit just so I can show you some of the work. So the first thing I'm actually going to do on this triangle, just because we are in the habit of using A, B, and C, is I'm just going to go and relabel these 3 vertices. We need to be comfortable with seeing them, but I think this is a tactic that we could also readily use. Just kind of rewrite these 3 angle measures to refer to as A, B, and C. Just as we are learning these laws, the law of cosines and the law of sines. So technically I have the measure of angle C. I have the length of the side that's opposite of angle A, so I'll call that lowercase a. And I have the length of the side opposite of angle B, so I'll call that lowercase b. So when solving these triangles, lesson 23-4 tried to show us that we could figure out, based on the given information, a good route to take. So looking at 5A, we have the length of 2 sides and an included angle. So this is what we refer to from that chart on lesson 23-4. This is known as side angle side. Again, we're not talking about congruent triangles or similar triangles for that matter, although this is based off of similar triangles. We're talking about the fact that we have 2 sides and an included angle. So if we go back and reference our chart from page 327, we see that if we have 2 sides in the included angle, law of cosines is our best bet as we start solving this triangle. And another way to know that is we don't have an angle and its opposite side measure. So we're missing angle B, even though we have its opposite side length. We're missing angle A, even though we have its opposite side length. But we know angle C, but we don't know its opposite side length. So that's a good indication that we're going to use law of cosines. So in fact, the first thing I'm going to do is go and find our third side using the law of cosines. So I'm going to go and also label this lowercase c. So we're finding C, if you will. So we're going to use the law of cosines that is set equal to C. So this is number 5. So C squared equals A squared plus B squared minus 2 times A times B times the cosine of C. So again, we don't know what C is in this problem, so we'll leave that unchanged. And A11 we called A, 14 we called B. So 11 squared plus 14 squared minus 2 times 11 times 14 times the cosine of, and I just forgot the angle measure, 34 degrees. So I'm going to go ahead and work left to right using PEMDAS. Good old PEMDAS comes back. So 11 squared is 121. 14 squared is, I believe, is 196. Minus 2 times 11, which is 22, times 14, which is 308, times the cosine of 34 degrees. We're going to go and add these 2, and I know some of you are still thinking, well, you have to multiply first. You're absolutely right, but when it's separated by this subtraction, it kind of gives us the authority or the capability to go and add these. It won't affect the overall answer. So we're going to go and add 121 and 196, and we get 317. So at this point, I know if I multiply 308 times the cosine of 34 degrees, I'm going to get a decimal. And so to avoid rounding throughout the problem, I'm going to go ahead and key this entire expression into our calculator. So 317 minus 308 times the cosine of 34. So 317 minus 308 times the cosine of 34. And we get 61.656. Now, this is what c squared is equal to. So we still have to take the square root to find the actual value of c. So we're going to give a couple decimals here, just a little breathing room. So 61.6564. The more decimals you can actually utilize, the closer to the final answer we will be, or the exact final answer. So now I'm going to take the square root of both sides so I can find the measure of angle, or not angle, excuse me, the measure of c. So now let's take the square root of that answer. So we see that rounded to the nearest tenth, because we are finding a side length, the 5 tells the 8 in the tenths place to round up. So the length of C is approximately 7.9. So we have just now found our third side. So we have the capability now to use either law of sines or law of cosines, because now we have a complete proportion for angle C and its opposite side length. I tend to use law of sines probably as more often than the law of cosines if I can. It's just a route that I'm more comfortable with. But of course, you can find the measure of angle B using the law of cosines, but I'm actually going to use the law of sines. So now that I have a full ratio, really, because I have the measure of angle C and its opposite side, I'm definitely going to use the sine of 34 over 7.9. So the sine of angle C over its opposite side, 7.9. And now it just greatly depends on which angle you would like to find first, because we actually have the length of the side opposite of angle B, so we could find angle B first, or we also have the length of the side opposite of angle A, so we could find angle A first. So we'll just go and find angle A since it's first in the alphabet. So the sine of A over its opposite side length, which is 11. Now we're going to cross multiply. We'll get 7.9 times the sine of A equal to 11 times the sine of 34. And again, at this point, you can go ahead and change that. You can multiply 11 times the sine of 34, get a decimal. I just think, well, if we have a calculator that can hold all those decimals without rounding, let's just leave it as the sine of 34. So the next step, our goal is to get sine of A by itself. So we're going to go ahead and divide both sides by 7.9. Because that is 7.9 times the sine of A. So on this left-hand side, of course, that will cancel out. And we will have the sine of A equal to 11 times the sine of 34 degrees over 7.9. Now, recall when we learned sine, cosine, and tangent, we use the inverse trig functions when actually finding angle measures. So if we see the sine of A is this ratio, we're going to take, say we're solving for A, of course, we're going to take the sine inverse of this ratio, and that is going to give us our angle measure. So the measure of angle A will be the sine inverse of 11 times the sine of 34 divided by 7.9. So let's use our handy dandy calculator for that. So the sine inverse, I'm going to go and do parentheses, 11 times the sine of 34, close parentheses because I want it to multiply, then divide by 7.9. So we get 51.1, and recall they wanted us to round angle measures to the nearest degree. So the 1 in the tenths place tells the 1 in the ones place to stay down. So the measure of angle A will be, and I'll go and add measure of angle A, will be 51 degrees. So now we have just found the measure of angle A is 51 degrees. And of course, you could use the law of sines again to find the measure of angle B the same way, but we have another theorem that tells us all three angles of any triangle in the world as equal 180. So the measure of angle B is equal to 180 minus one of our angle measures minus the other angle measure. So the measure of angle B is 180 minus 51 minus 34, which is none other than 95 degrees. So the last thing I'm going to show you on this particular item is how to make sense of your answers. So on A, which angle is the largest angle? Well, it's the 95-degree angle at B, or which was originally R. So notice which side is the largest side length. Well, it's what we labeled lowercase b, which is 14. The larger the angle measure, the larger the side length opposite of that angle. So as you're solving these triangles, make sure your answers are reasonable. So conversely, which is the smallest angle measure in 5A? Well, it's 34 degrees. And notice what the smallest side length is. It's 7.9, the side opposite of that smallest angle. So just keep that in mind as we're solving these triangles to make sure our answers are reasonable. So now let's take a look at item B and see how it's a little bit different than A. So on item B, again, what I'm going to do is I'm going to rewrite these three angles just in alphabetical order as A, B, C. Don't feel like you have to do that, but just when we're using law of sines, law of cosines, most students are more comfortable when we actually write the laws using A, B, and C. So this is just a tactic that I think could help. So again, opposite of angle A, we'll label 15 as A. Opposite of angle B, we'll label 6 as B. And opposite of angle C, we'll label 10C. So notice what we have here. We have no angle measures, but we have all three sides. So this is side, 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 which if we go back to our chart on the previous page, we see that side, side, side. We're going to use the law of cosines to find initially an angle measure. So it doesn't matter which of these angle measures we decide to find first. More than likely, we'll just go with angle A because it's first in the alphabet. So if we're looking for angle A, we have to use the law that contains or uses angle A, which is actually set equal to its opposite side length squared. So for 5B, so this is actually 5A, I should say that. Notice I kind of erased the work here just to give us some space. So for 5B, we're going to use the equation set equal to A. So A squared equals B squared plus C squared minus 2 times B times C times the cosine of A. And again, that represents the measure of angle A. So the reason we're using this law is that it finds the measure of angle A. So let's see what those measurements are. A is 15, B is 6, and C is 10. So A is 15, B is 6, and C is 10. So I'm going to replace B and C here, of course, with 6 and 10, and cosine of A. So our first task is, of course, to simplify the math that we actually can, and then we need to get cosine of A by itself so that we can solve for A. So we'll start actually squaring these values here. So 15 squared is 225, 6 squared is 36, 10 squared is 100, and we'll multiply 2 times 6 times 10. 2 times 6 is 12, 12 times 10 is 120. So we can go and add these two here. Not sure what happened right there, but seemed to fix itself. So we get 225 equals 136 minus 120 times the cosine of A. So remember, this is a technically 136 minus 120 times the cosine of A, or another way to look at it is negative 120 times the cosine of A. So we are going to start by getting this term by itself by removing the 136 that is technically being added to this side because it's a positive 136. So we're going to subtract 136 from both sides. And so 225 minus 136 is none other than 89. So of course, I'll show that it cancels. So we have negative 89 equals negative 120 times the cosine of A. So now we are going to divide, since this is negative 120 times the cosine of A, we're going to divide by negative 120. And of course, that division will cancel that multiplication there. And so really the only thing that we're going to do between these two terms, although there might be a term that both of these can be divided by evenly, we're going to simply say that a negative 89 divided by a negative 120 is a positive 89 over 120. Because when you divide a negative by a negative, it is a positive, equal to the cosine of A. So we've done this several times, but if you still need to try to wrap your mind around this, if our goal is to find the measure of angle A, we're going to use the inverse trig function. And of course, since we're using cosine, we're going to use the inverse cosine function. So A, the measure of A, I'll actually go and write the measure of A because we're talking about an angle, is the inverse cosine of that ratio, which is 89 over 120. So now we'll use our handy dandy calculator. Sorry that I keep calling it a handy dandy one, but it is rather handy because it does some pretty incredible math for us. So cosine inverse of 89 over 120. So cosine inverse of 89 over 120 yields 42.1. Remember, we're rounding to the nearest degree, so the 1 in the tenths place tells the 2 in the ones place to stay where it is. So it is 42. So the measure of angle A is 42 degrees. So I'll go and add that to our diagram here. So at this point, we have measure of an angle and its opposite side, which opens the door to law of sines, which, as I said before, I find that to be the easier law to use other than law of cosines. But again, at this point, you can find the measure of angle B doing the exact same thing we did here with the law of cosines. But I'm going to use the law of sines now since we have measure of an angle and its opposite side. So I'm going to do that work. I guess right here would be just fine. So we're going to use the sine of A for sure, since we have the measure of the angle A and its opposite side equal to, let's say we're solving for angle B next. So we're going to use the sine of B sine of B over its opposite side, which is 6. So we do the sine of B over B. So let's replace with what we know. We just found the measure of angle A was 42 degrees. So we'll replace A with that. The length of A is 15. Sorry, I keep going back and forth. Got to make sure I write the correct values. We're finding angle B, so we'll leave capital B alone, and lowercase b is 6. So the reason I love law of sines is it's fill in, cross multiply, maybe a little division. And in this case, we just have to do one extra step of doing the inverse sine. So we're going to cross multiply here. We'll get 15 times the sine of B equal to 6 times the sine of 42 degrees. Now I'll say it again. You can go and put this right side in the calculator and get a decimal form of it. But since our calculator can hold the decimal form without rounding, I'm just going to leave this as 6 times the sine of 42. Well, if this is 15 times the sine of B, our first goal is to get sine of B by itself. And so to undo that multiplication, we are going to divide both sides by 15. So in doing so, on the left side, it of course will cancel out that multiplication like we wanted it to. And we'll be left with the sine of B is equal to 6 times the sine of 42 degrees over 15. Now, at this point, to find the measure of an angle, we're going to take the inverse of this trig function, which if we're using the law of sines, of course, we'll use the inverse sine function. So B is equal to the sine inverse of this ratio. I know it looks like a crazy ratio, but a ratio is just a comparison of two numbers, and this is a number, and this is a number. And so it's a ratio. So the sine inverse of 6 times, and I'll go and write the measure of angle B because that's technically what we're finding. 6 times the sine of 42 over 15. So don't forget to do the sine inverse. You'll get a really weird answer if you don't. So the sine inverse I'll go and put an extra parentheses, 6 times the sine of 42 divided by 15. And again, we are finding an angle measure, so we're going to round this to the nearest degree. So the 5 in the tenths place tells the 5 in the ones place to go ahead and round up. So the measure of angle B is 16 degrees. So let's go and add that to our diagram here. So then we can hopefully piece together the last and final way to find the measure of angle C. Well, of course, you could use any of the methods, law of sines, law of cosines. We see that now. But the easiest method at this point is that all 3 angles of any triangle have to add equal 180. So to find the measure of angle C, just so I can show you the work, we'll take 180 degrees because that's the total sum of all 3 angles. We'll subtract the 2 angle measures we do know, and we'll find the measure of angle C. So 180 minus 42 minus 16 is 122 degrees. Now that looks off, so let's just make sure that our work is actually correct. Maybe, no, sine inverse of 6 times 40, the sine of 42 over 15. So let me just check, make sure, because that value does look a little bit off. So this is one of those instances where it's great that we actually show the work here. So back in this original problem, my board did something pretty interesting, and I mistook it that I had a negative 89, which if I just slowed down a little bit, I realized that that should have been a positive 89. So it's a positive 89 divided by negative 120, which will still be a negative 89 over 120. So when I actually should have found the measure of angle A using the cosine inverse, I should have done a negative 89 over 120. And I can't believe I didn't catch that. We are, of course, not perfect. And even math teachers that have been doing this so long, we tend to make some mistakes. So let's go correct the measure of angle measure of angle A, which is clearly not 42. Not sure what happened there. Sorry, my board was acting up a little bit. So let's go and fix this. I believe we had, even still, it's acting up a little bit. So let me fix that. So we got 89 equal to negative 120 times the cosine of A. And my mistake was costly right here. I mistook it for a negative 89. So we got the cosine of A is equal to negative 89 over 120. And I know some of you watching this, you were like, I thought it was a positive. I can't believe you messed up. Hopefully you kind of kept going the proper course, even though I made a mistake here. So we're going to take the cosine inverse of the correct ratio. So this is the measure of angle A equals the cosine inverse of this ratio, now negative 89 over 120 instead of a positive 89 over 120. So the measure of angle A, let's go and change that on Desmo. So it should be just a quick little change here. Negative 89. That seems like a much more reasonable answer. 137.8. The 8 tells the 7 in the ones place to actually round up. So the measure of angle A is vastly different than the original we found, which would be 138 degrees. Which, if you think about it, this is pretty interesting to find out. The original measure that I found was 42 degrees, which if you add 138 degrees and 42 degrees, you actually get 180. So that is that's interesting how we found that to be the case here. Although I'm not necessarily sure what that leads into, but rather interesting to find. So let me go and correct that measure of angle A is 138 degrees. So over here in the law of sines, I just simply erased 42 degrees. I'm going to go and change it to 138. So now we're going to divide both sides. We'll get, of course, that will cancel. the sine of B is equal to 6 times the sine, 138 degrees, now that we fixed that, over 15. So again, to find the measure of angle B, we're going to use the sine inverse. So I'll say measure of angle B is equal to the sine inverse of 6 times the sine of 138 degrees over 15. So let's find the measure of angle B now that we have the correct angle measure for A. So I'm going to go in and just simply change 42. Nice thing about a graphing calculator is it holds our work to 138. And we get 15.5, which if I'm not mistaken, is still the measure we thought it was just a moment ago. So, which is 16. But of course, the measure of angle A, very, very important. But that's interesting how, even though we have a different angle measure, 138 or 42, we still get the same result here. So the measure of angle B is 16 degrees. So let's go and add that to our diagram. And so I should have caught it to begin with, but what helped me catch it was the length of this side is 15, the largest length. So opposite of that should be the largest angle. So that's how one way I knew that my answer wasn't reasonable. And it took me a second to realize where I made the mistake. And again, the smallest side is 6, so opposite of it should be the smallest angle. So this should definitely be, measure of angle F, or what we're calling C, should definitely be greater than 16 degrees. So the measure of angle C is equal to 180 minus 138 minus 16. So let's find the measure of angle C with a little simple subtraction. And we get a much better answer for what looks like an acute angle, 26 degrees. So the last one I'm actually going to work of 5 is item D. Simply put, because item C is just a reiteration of what we did on A. It is side angle side. So we're going to see how item D is just a little bit different, and hopefully I'll have enough room right here to do that work. So fortunately for us on item D, it's already labeled, the 3 vertices are already labeled A, B, and C, which we're comfortable with. So I'm going to go and label their opposite sides. So opposite of angle C will be C. So we don't know the length of C. We don't know the measure of A or its opposite side, but we do know the measure of angle B and its opposite side, which already makes me think that we're more than likely going to use law of sines because we have that complete proportion there, or complete ratio rather, to use a proportion. So we have 2 angle measures and what's considered a non-included side, which I actually told you is a cuss word backwards. So side angle in this case, if we go back and look at our chart, tells us that we're going to use the law of sines to help us solve this triangle, which, as you know, if you've seen this lesson practice, you know I really lean more towards the law of sines. So since we have the measure of angle B and its opposite side, of course, we're going to use the sine of B over B. And since we know the measure of angle C, we definitely need to go and find its opposite side. Although it would be rather simple for us to go ahead and find the measure of angle A, considering all 3 of these angles will add equal 180. So we can do that initially if you would want to pursue that route. So find the measure of angle A, I'll just do that work here. 180 minus 115 minus 52. And we get the measure of angle A is 13 degrees. So now, truthfully, at this point, there are other options we could take because now we have angle side angle. And so that opens the door potentially for another route. But we'll continue with the law of sines here. So again, we're going to go and find the measure of C because we initially had angle C to start. So we'll set sine of B over B equal to sine of C over C since we're looking for C. So I'm going to replace all our known values, sine of 115 degrees over its opposite side length, which is 24, equal to the sine of 52 degrees over its opposite side length, which we don't know yet. So we're going to cross multiply. So we'll have 24 times the sine of 52 degrees equal to c times the sine of 115. Even though I forgot the c times the sine of 115. And since our goal is to find the length of c, and this is c times the sine of 115, we're going to go and divide both sides by what we're multiplying by, the sine of 115. So when you divide by what you're multiplying by, it cancels. And so the c is equal to 24 times the sine of 52 degrees over the sine of 115 degrees. So now we're going to use our wonderful magical calculator. Notice I didn't call it handy dandy. Wonderful magical. It doesn't have much of a ring to it, but that calculator to evaluate what this equals. So 24 times the sine of 52. So I'm going to go and put in parentheses just in case. 24 times the sine of 52, close parentheses, divided by the sine of 115. Which we are finding the length of a side, so we're going to round to the tenths place. So the 6 in the hundredths place tells the 8 to round up. So the length of C is approximately 20.9. So let's go and add that to our diagram. And so the last thing we need to find, because we have all three angles already, is we need to find the third side. And so I'm going to use the law of sines again, because I know the measure of angle A, and I'm looking for its opposite side. So we'll continue with the sine of B, which we'll use the sine of 115 degrees over its opposite side. I typically use the values that we're already given. You know, this is a rounded value. I know we're kind of, sometimes our hand is forced into using a rounded value, but avoid it at all costs, just so we're closer to the exact answer as possible. So now if I'm looking for the length of A, I'm going to use the sine of A, which would be the sine of 13 degrees over its opposite side length, which we don't know. So let's repeat the process. Hopefully we're doing this so much that we understand the process, understand why we're using the law of sines, when we're using the law of cosines, and really just a continuation of how to solve what looks like very complex work. But we're going to cross multiply here and get 24 times the sine of 13, excuse me, and A times the sine of 115 degrees. Since this is A times the sine of 115 degrees, and we're trying to get A by itself, we will divide by what we're multiplying by, the sine of 115 degrees. So that will, of course, cancel. And we'll use orange here. So A will equal 24 times the sine of 13 degrees over the sine of 115 degrees. So let's find out the approximate value of A, 24 times the sine of 13 divided by the sine of 115. And I already forgot it. 24 times the sine of 13. 24 times the sine of 13 divided by the sine of 115. Again, we're rounding to the nearest tenth. We got an interesting one here. The 5 in the hundredths place tells the 9 to round up to 10, which means the 5, in fact, becomes 6. So rounded to the nearest tenth would actually be 6.0. So the length of A is 6.0. So as stated before, we are going to skip C, although it's great practice. It's just like item A, so probably going to use the same route because we have two sides in the included angle. So let's complete 6, putting it back in context, kind of like how your test will be. So it's always good to see these problems back into a real-world context. So 2 lifeguards on the towers at vertex A and vertex B are watching a swimmer in the ocean. There's a swimmer here at vertex C. Which lifeguard is closer to the swimmer. So the reason I love this question is it doesn't say, hey, find the distance, but we should use context clues to understand that that is what we're doing. So if someone is closer, that means their distance is less. So we are trying to find who is actually closer, and we could probably go ahead and create an estimate because we understand angle measures and their opposite sides. In fact, if this is 37 degrees, its opposite side length is definitely going to be shorter than the length of AC, opposite of a 45-degree angle. But nonetheless, they ask us to show our work, so we're going to prove that it is, I guess you would say. We'll start by finding the measure of angle C. Because we have its opposite side length, I believe that's going to help pay off here. So to find the measure of angle C, just so you see the work, we'll take 180 minus 37 minus 45. And we'll get none other than 98 degrees, just like the band. If anybody knows the band 98 degrees, pretty old. Try to be like NSYNC, but anyway, let's talk about lifeguards and swimmers. So the reason I went ahead and found the measure of angle C is because now I have all three angles in one side. In fact, I have the side opposite of one of the angle measures. So this lets me know that I can use the law of sines. So since we have angle C and its opposite side, we're definitely going to use the sine of C over its opposite side equal to, and it all depends on what you want to find first. But I'll go ahead and label that this is A, opposite of angle A, and this is B, opposite of angle B. So we'll go and find A since it's first in the alphabet. So we'll set this equal to the sine of A over A. I'll replace it with known values, of course. So the sine of what we found was 98 degrees over its opposite side, 500, equal to the sine angle A is 37 degrees over its opposite side we're solving for. So hopefully getting used to this process, I know I am. So we're going to cross multiply and we'll get 500 times the sine of 37 degrees equal to A times the sine of 98 degrees. So pretty quick here, since we don't have to take the inverse sine because we're not looking for an angle. Since this is multiplication, we will divide to get A by itself by the sine of 98 degrees. This, of course, on the right-hand side will cancel or become the number 1, truthfully. It'll be 1A, so that's why we call it cancels or, get rid of it, but it really becomes the number 1. So A is equal to 500 times the sine of 37 degrees over the sine of 98 degrees. So we'll use our wonderful magical calculator to evaluate the length of A, its approximate distance. 500 times the sine of 37. So we'll go and put it in parentheses just in case our calculator wants to do something weird, divided by the sine of 98. And we get 303. Let's see what, if they asked us, probably didn't really ask us to round to anything because they're really just wanting to know who is closer. So we'll just continue, since it's a side length, round to the nearest tenth. So the 6 in the hundredths place tells the 8 to round up to a 9. So we'll have 303.9 feet, since we are dealing with an actual unit here. And so we know that the distance from lifeguard B to the swimmer is 303.9, which is a reasonable answer because look at one of the distances already in our triangle. Otherwise, I'd probably say that it's a very outlandish answer, but it does seem to be okay here. So now let's find the length of B doing that same process. So again, I'll use sine of C simply because we didn't have to round for any measure about its angle or its opposite side. And now that we're finding the length of B, we'll use the sine of its opposite angle to find its side. So let's replace with known values. So the sine angle C is 98 degrees. over its opposite side length, which is 500, equal to the sine of B, which we know angle B is 45 degrees, over its opposite side, which we don't know. Now let's cross multiply, and we will get 500 times the sine of 45 degrees equal to B times the sine of 98 degrees. Last step here, this is nice that we don't have to find an angle measure. We just divide by the sine of 98 degrees. Of course, I'll show that it actually cancels. And we will be left with B equals 500 times the sine of 45 degrees over the sine of 98 degrees. So let's find what is B approximately. 500 times the sine of 48. Make sure it was 40. Oh, it's 45. 500 times the sine of 45. So I'll put in parentheses. Divided by, close parentheses before I divide, sine of 98. And we get 357.0. The 2 tells the 0 to stay what it is. So we'll say that the distance from A to C, which we call lowercase b, is 300, and I believe it was 57, but let's just make sure. 357.0 feet. Because we actually have a unit now. So I think our hypothesis was correct. We do, or I guess our educated guess, if you will, that the lifeguard at Tower B is actually closer to the swimmer located at C. Now, for those that, there might be a theorem out there, but we haven't definitely come across that theorem that tells us that the side length, it's connected to the angle measure. And so whichever angle measure is the lowest angle measure, the smallest angle measure in the triangle, its opposite side is the smallest length. So for those that wanted to just kind of summarize this very quickly and say, well, we know Tower B is closer to the swimmer at C because the measure of angle A is the smallest angle in the triangle. There might definitely be a theorem or even a postulate concerning that, but there's not one that we have stated clearly. So of course we need to show this work here to prove that in fact is true, that Tower B is closer to the swimmer at vertex C. So that is the end of the lesson 23-4 practice and the end of activity 23. There is an activity 23 practice on the next page. I encourage those to continue practicing through this work. Hopefully more and more practice will solidify which process to use and how to complete that process. But hopefully this lesson practice helped. Thank you for watching.